Example of the p equal 3, so then p equal 4. It's a quiz. Why don't you bring the one question? So in this case, the p is equal to 4, and it's a B3 structure. So this will be like the, how many children pointer? How many children pointer? 1, 2, 3, 4 children pointer. And how many index key entry?
3.
1 less than p. So we have the 3. Okay, this is our node structure. So we are going to use this node structure. It's exactly the same thing. When you implement the B3 or B plus 3 structure in programming, okay? So you need to design, okay? Design that node structure. So this node structure will be implemented in your programming. Okay? This is just nothing but visualization. But in your programming, you can do the same thing. Like it can be class, it can be function, it can be struct. Okay? Then, after this, we are going to insert the string. This is a simplified one. We don't give any additional data, but it can be easily, like the insert something into values, and the 8. 8 is the key. Then other information. This is a simplified. So first we are going to insert 8. So 8 is here. So this is a data pointer. Okay, data block. This is an index. Index is helping to access the data block fast, right? So there is always the data block, data structure, table structure. So this is a pointer to the data blocks. Okay? Then once 5 is inserted, so still we have a room. So 5 and 8. Then 1 is inserted, still we have a room. 1, 5, 8. Okay, that's it. Then next one is the 7. When 7 is inserted, it's a full. Okay, so in case of a full, what? It's a split. So 1, 5, 7, 8. First we need to find middle value. So middle value is a 5 or 7. In our class, it's a 5. Cut in half and left hand side. So then next operation is what? The left hand side, right hand side, we are going to split into 2. Then middle value will be promoted. So 2 main operation. So split into 2. And this is the another index node. So 1 and 7 and 8. And middle value will be promoted after this. And this is a 5. Don't forget to finalize children pointer. And this is the children pointer. Okay, this is up to 7. And 3. Even though we have empty node, empty space in the root node, we are not going to use this one. Always find whether they will use the 3. Search this. 3 is less than 5, goes to here. So there's no 3, so we can insert and we have space 3. 12 is the same. Bigger than 5, goes to here, there's a space 12. And 9. 9 is bigger than 5, but there's no space. So this is the full. 7, 8, 9, 12. So 8 is the middle value. So middle value will be promoted 8, and this one will be split into 2. So we have this one. This. So 7 and 9, 12. Then less than 5 goes to here, bigger than 5, less than 8 goes to here, and bigger than 8, greater than 8 is equal to last one. Okay? So this is up to 9. And 6 is bigger than 5, less than 8. So it should be here. So 6 and 7. And 0 is less than 5. We have a space 0, 1. So this is the final out. Any question? Maximum 10 point. Okay, nothing 0 point, and you can give the partial point. So finalize and submit right now. So maximum 10. Okay, that's great. Mandy? No? So up here?
Professor, that example would be equal to 4, right? That example would be equal to 4.
Yeah, it's equal to 4. It was a homework, but I thought the last class was on Monday. So I said the due date is Wednesday, so I'm going to cancel the homework. Instead, I did the quiz today. Okay. Is it yours? Professor? Oh, okay. So you're trying to Okay, so why do we build a B-tree index instead of a search tree? So search tree usually it can be easily skewed data. Skewed tree. For example, we have tree like this. So which means when we access the data block using these trees, sometimes 1, 2, 3, 4, 5. Sometimes 1, 2. Okay? And also it can be extremely skewed tree, so that doesn't guarantee how long it takes to access the data using that index, which is not good. So we need balanced tree, that is a B tree. Main difference is what? This one is building top to bottom. It increases from top to bottom. But this one, as you have seen, is a bottom to up. So any node, any leaf node has 1, 2, level 2 in this case. It's the same level. However, when you access the data using this index, for example 5, how many IO then you need? How many IO? 1 and 2, because this is the data pointer, so we have the data block like this, 0, 1, 2, 3. So for example, this one is this. What about 3? 1, 2, 3. Okay? Which means it has upper bound. Okay? That is the same as level of leaf node, degree of this tree. However, it's equal or less than this level, which means sometimes 2, sometimes 3. It's not fully, completely balanced. Okay, even though it's better than the search tree, still It's not completely balanced. That is the same as this one. In case you travel from the Bridgeport to the New York, okay, Manhattan. So maximum, so if you are lucky, you can see the schedule for the MTA. Sometimes it takes 1.5 hours, sometimes the 68 minutes if you are lucky, okay. It cannot guarantee the exact time, but it shows the maximum 1.5 hours, 90 minutes. But depending on the time, depending on the schedule, it can be less than that. So we cannot set up the appointment 1 hour later, okay? We should have the maximum. That's the same problem. In case we have the, for example, B3 level is 100, okay? So still, sometimes we need 101 IO or 2 IOs. So in terms of the DBMS engine, DBMS, especially theory optimizer, I'm not sure whether this index provides very fast time or slower time. So we need completely balanced tree. That is the B plus tree. What is the idea? Any idea? How can we build the completely balanced B plus tree? Any idea? No idea? Why don't we move all these index key entry to the leaf node? So always when we access the data block, we need to visit leaf node, which means in this case 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? Instead, so this is called in terms of the tree structure, data structure, this is called the leaf node. So leaf node has the all index key entry node. What about this one? Root node, and this is called internal node. Okay, non-leaf node. Non-leaf node do not have index key entry. Instead, it has just the separator, split the data only. Okay? So to satisfy such a condition, in B3 index, we have only, in case of P is equal to 3. This is a B3 node. However, B plus 3 node, the leaf node and internal node are different, right? Leaf node has what? Key entry. On the other hand, the internal node has only splitter. So, first, the leaf node, do we need a child of leaf node? Leaf node of the tree structure is always terminal node, which means there is no child. So we don't need this one, right? Instead, we need only index key entry. That's the different thing. And also, what about the internal node? Internal node, we don't need the index key entry. Only we need splitter, like this one, child point, children pointer. So, children pointer, how many children pointer? By the way, P, okay? What about the leaf node? How many index key entry? P minus 1, okay? It's the same as the B3 index. So, we need this. Then, only key value. So, we don't have to make that this one, just this. There's no data pointer, only children pointer. Okay? It looks like the B3 index, leaf node, and internal node is the separation of B3 index. Okay? One more thing. There is another thing, this. This is a pointer. Address pointer. I will explain later. Why do we need this one? That's another benefit, important benefit of the B plus 3 index. Then we are going to study to build a B plus 3 index using the same, the index key entries. Okay? Idea is the same. In case of full what? Split into 2. And then the middle value will be promoted. However, that promotion is slightly different. So first we are going to start. There's nothing A is inserted. Which one will be used? Internal load or leaf node? Internal load does not have index key entry. It will be used for splitter. So we don't have to split the first time. We need only leaf node. So this one. And 8 and 5. Okay? The 8 and 5 is inserted, this one. Then, what about that? 1 is inserted. So 1 is inserted. Any space? So this is a full. Right? In case of full, we need to split. So 1, 5, 8. We need to decide the middle value. This one. So we are going to split into 2. This. Left hand side. In case of B3 index, this is the left hand side. And this is the right hand side. However, in case of B plus 3, as we decide, all index key entry will be in the leaf node, which means 1 and 5, including middle value. 1 and 5 will be left hand side. And the other, right hand side. So 8. This is a split. So split is slightly different. Okay? B plus 3, only less than middle value will be left hand side. However, the B plus 3, because we are going to keep all index key entry in the bottom. Okay, so 1 and 5, including middle value. Then we need to split into 2, right? So promotion will create the internal load only. Then middle value will be copied, 5. However, this 5 is different from this 5. This 5 is what? Index key entry. This 5 will be used for splitter. Okay? Equal or less than 5 goes to here. And greater than 5 goes to here. This is the B plus 3. Then check. When you access the data, 1, how many are you? 1, 2, 3. And what about 8? 1, 2, 3. What about 5? 1, there's no data pointer. This is just used for splitter. So equal or less than 5 goes to this one, and 5 and data pointer. How many? 3 ions. Any data has the same number of ions. So completely balanced. The next, 7. 7 is bigger than 5, and here we have space. So 7 and 8. And 3. 3 is less than 5. And here is a full. So 1, 3, 5. Which one is the middle value? 3. So equal or less than. This one is the left hand side. This is the right hand side. So we split into 2. 1, 3, and 5. Then middle value 3 will be promoted, but this promotion it's not exactly same as the B3. It will be used for splitter. So 3 and 5. Equal or less than 3 here. Bigger than 3, equal or less than 5 goes to here. Bigger than 5, greater than 5 goes to here. Any questions so far? It's clear. 1 except 1. What about this one? This is a pointer to this. It's called the sibling pointer. Sibling pointer. Why? Because all index key entries are leaf node. So when you count from the smallest one to highest sequentially. The search 1, 3, and then 5. You can use the sibling pointer because it's ordered. If you are looking at the only leaf node, it's ordered. Right? What about this one? You need to up and down. 1, 3, 5, 6. You need to up and down in B plus B3 index. However, here, because all index key entries are in the leaf node, we can use such a sibling pointer. So that is the another main difference thing between the B3 and B plus 3. For example, when we select the data from this table, let's say this is an employee and this is an employee ID, is greater than 0. If you are using this index 1, 3, then 5, you can use the leaf node only. However, what about this? You need to 5, 1, 3, 5, you need to search every time. In this case, the difference is quite small, but if you have the huge tree, it's a huge difference. Okay? So that is a sibling pointer. So don't forget the sibling pointer. Okay, this is up to 3. What about 12? So we have space, but we cannot insert 12 here, 12, then goes to here. So it's a full 7, 8, 12. Which one is the middle value? This one, left hand side, right hand side. Like this. And 7 and 8, 12. Always you need to check the, what about this one? 8 is, should be, supposed to be inserted, but we do not have space. So it's a full, so we can split. 3, 5, 8. First, split. Which node? So still internal node. This one. Still internal node. Which one is the left hand side? 3, 5. We don't need 5 here. The reason why we include the middle value is we try to put down all index key value. This is only for splitting the data, right? So this is a middle value and left hand side, right hand side. So 3 and 8. This is a 5. So less than 5, bigger than 5, and equal or less than 3, and it's a, what about this one? 5 will be this one or this one. This is a less than 5. This is a bigger than 5. So bigger than, equal or less. This is equal or less than 5, right? Left hand side is always equal or less. So this is supposed to be this, the children node. And 8 and 12. Don't forget sibling point. So this is the same as what? B3 index. That this split and promotion is the same as this one. This is a common mistake. 5 is not part of the internal one. Okay? The next, 9. 9 is bigger than 5 and bigger than 8. So 9 is supposed to be here. And 6. 6 is bigger than 5, less than 8. So supposed to be here. Even though we have space here, there might be no problem even though we insert the 6 over here. But this side is equal or less than 5 point. Okay? So this is supposed to be here 6. So 9, 12, and this is the 6, 7, 8. So 6, 7, 8. So 7 should be promoted. This one. and 7 input. This is the output of B plus 3. Always check. What about 5? I'd like to access. Select the data 5. Can you find the data node from here? No. You need to always visit the leaf node. 5 equal to 5 goes to here. And 5 is greater than 3 and goes to here. And 5. So using this pointer, you can access data 5. Data block. Okay? Not from this one. This is only used for splitting the data. Okay? Okay. Any question? What about 0 is inserted? Another quiz. Okay. Another quiz. I will give a chance to make up the last one. The question? So why don't you use XI? Okay. So you say inserted. First, you need to decide where it goes. So 0 is equal to or less than 5 and equal to or less than 3 and supposed to be here. But it's a full. So 0, 1, 3, that's great. So decide the middle value that 1 and equal, including middle value and left hand side, go to the left hand side node and the other right hand side node. So we need to split into 2. And 0 and 1. This is 3. Okay? So split. The middle value 1 will be used the first splitter, so promote 2 here. So insert 1 and 3. Okay? Then we arrange all children pointer. So equal or less than 1 goes to here, and bigger than 1 equal or less than 3 goes to here, and bigger than 3 equal or less than 5 goes to here. This is the after 0 is inserted. Okay? 10 points. Then another problem, what if 13 is inserted? So you need to decide which leaf node will be used for 13. So greater than 5, greater than 8, this one is supposed to be. But it's a 4, 9, 12, 13. So this is a middle value, including middle value, left hand side, and the other right hand side. So we need to split. So let's use this one and this. So 9, 12, 13 will be used, and 12 will be inserted here. It's also full. So internal node, we can follow the B3 index because we don't need to keep the middle value in the left hand side. So only the children pointer 7, 8, 12. Then 8 will be promoted. Then check all the children pointer. Then left hand side is okay. The greater than 5 goes to here. The greater than 8 goes to here. And less than 7 and bigger than 7 and equal or less than 8 goes to here. And less than 12 goes to here. Bigger than 12 goes to here. Okay? Then don't forget the sibling pointer. This one, this one, this one. Okay? So this is the final output after inserting the 13. Another 10 point. Okay? Wasn't great? Then any question? Then what if we access the data 7? Okay? Data 7, we need to decide the leaf node, not the internal node. The internal node of the B plus 3 will be used for only the splitter. So bigger than 5 and less than 8, this one. And the 7 is equal or less than 7, goes to here. The 7 is here. 1, 2, 3, and one more at the data node. So 4 IOs are needed. We will use this technique during the query optimization. If we are using the index B plus 3 index, how many IOs are needed? Then decide whether this is faster, this is slower. So we will learn during the query optimization. Any question? Okay. So don't forget to write your name. The next topic is to finalize the data file and the index file. The next topic is the functional dependency and normalization. Is there anyone who ever heard about before you are taking this course, normalization? Before? What is the normalization? In general, what does that mean, normalization? Like the normal distribution. What is the normal distribution? Minimization? I don't think so. Have you ever heard about Gaussian distribution? What is the Gaussian distribution? It's the most general distribution, like this. You have seen this one, right? It's a Gaussian distribution. In general, in our real life, many of the events, we are going to call such a thing as an event in the statistics. So, usually, the common thing happen a lot, rarely happen the unusual case. So this is the thing. So, middle, this is the average. And this one is the wing side, so rarely happen. So this is called the Gaussian distribution. Gaussian distribution, think about if I grade the midterm or the exam quiz, it will form usually Gaussian distribution. Of course, average, many of the students form the average, rarely got the A plus, and rarely got the F fail. So that is the general event, general distribution. However, this is called what? Mu, in terms of the statistics, average. And what about this one? Sometimes Gaussian distribution like this, sometimes this. Okay? This is variation. So, using the Gaussian distribution need the two parameters only. One is the mu, average, another one is sigma, is the variation, or standard deviation. So that is the reason, if you read many technical paper or economic paper or the academic paper, many of them, 99%, they are using Gaussian distribution. Why? Because it's a general, and also you need only two parameter value to decide a certain event. So that is the Gaussian distribution. For that Gaussian distribution, if we transform the average, this average into 0, okay? So this is the 0. You can shift left or shift right. So if you transform your Gaussian distribution to the average is the 0, that is called normal distribution. So normal distribution, how many parameters do you need? Only one parameter value is a variation or standard deviation. So normal distribution means you can standardize you can make any event standardized. How we can standardize? Fit to the zero average. Then we can consider only variance. Okay, that is the normal distribution. So normal means in general standard. Okay, we can normalize. Normalize means standardize. So like for example, if you get the 100 marks in the quiz and midterm 100 marks, are they same? It's not fair, right? Because the quiz is just a simple 1 or 2 question, but midterm is the 20 something question is more difficult, right? If I give the 100 marks equally, it's not fair. So we need to normalize, standardize by considering the weight. So for example, I will give the 10% for the quiz and 90% for the midterm exam. So this is called also normalization. What about the normalization in database? Any idea? What is the main purpose of the database design?
Partition equally the table.
We'd like to access the data very fast. However, what if we have a lot of redundant information, a lot of leak, a lot of the computer science? When I search the student using major, a lot of computer science student, okay? There are a lot of redundant information. Also, think about if UB, University of Bridgeport, keep the student information by department. Each department has their own student information. Like your information is in the computer science department, your information is also in the HR department, your information is also payroll department. If you have the minor department, so that department also has your information. What if you move to the house? You need to inform to everyone, every department. It's a tedious. That should be doable, but what if you miss one of them? Because you have your information are duplicated a lot, it's very hard to manage, even not very efficient. So we need to standardize. How can you standardize the database? You can keep only one information about yourself, okay? Non-redundant information. What is the best way for the non-redundant information? Best way is actually we can keep the microdata. Microdata means, so for example, when we design the student table at the beginning of this semester, student consists of what? Student name, student ID, address, why don't we separate all attributes? So your name is one table, your ID is one table, your address is one table. If we split by the attribute, there might be no problem of the redundant. There's no way to redundant such information because you split everything, right? So that is called the standardization. That is called the normalization. So normalization in database means it's kind of process of the database design. One of the way of the database design to standardize your table, your information, to normalize your table. How? Why? We don't want redundant information. How we can do that? We can split, split, split. In other words, decompose, decompose, decompose. We can segment, segment, segment. That is called the normalization. So far we have designed the database using what? Conceptual modeling and relational modeling, and finally physical database modeling you can create. Another way is we can use normalization process to design the database. Also, normalization can be used for judging, decide whether our database is good enough. Because normalization itself is a mathematical process. So we can use that process to judge whether his database design is good enough. It will be used for goodness measure to decide, to measure how much good his database design is. Okay? In other words, whether there exists duplicate data or not. Okay? Using normalization process. So that is the topic of normalization. How can we do that? Using functional dependency. So we will see what is a functional dependency later. Okay? So, what is a good relation? What is a good database design? No redundant information. If we do not have the redundant information, that is a good database design. So, goodness. So, to do that, there are different ways to measure the quality of database design. So, for example, first one is semantic, is clear. And which means a student table has only student information, and department table has only department information. Semantically, it's clear, and where the no redundant, it's not possible. Sometimes 100% the redundant free database design as less as possible. So no redundant information and no null data. Why do we need a null attribute, null data? Why? What does that mean, null? Null means not existing. Why do we need to keep the information about the not existing? Doesn't make sense, right? It's not existing. Why do we need to keep such a non-existing the information in the database? Even that waste of space. To represent the null, we need to have a certain amount of the data, right? Even though it's not existing. Why? Have you ever thought about that? Why do we need to keep the null information in the database?
Maintain the structure of the table.
Yes, because the relational database model is easy and it's very fast. The problem is how we can keep such a fast, efficient, and how can we keep the consistency of the data using relational model? Because we clearly define, for example, student as ID, student ID, and name, and address only. This is our structure. Then all information about the student should fit to this one, no matter what types of student we have. Okay? For example, I do not have, for example, address. Okay? Then I have only ID 111 and name Lee. But this one is different from the student database design. Because there's no address, so you cannot keep this data actually. To address that one, we can make a fake data that pretend the same data structure. Because of this one, we can keep the very fast data accessing using relational model. Okay? So that is a null data. The more, the better? No, definitely not waste of space. Okay? Because of that, we need to reduce the as less null as possible in our database design. And sometimes we will see, sometimes when you join the two, the table which is not well designed, it will generate some unexpected data, okay, during the join. So all of these are actually from what? Because of redundant issue. So semantic one table and no redundant information, null as less null as possible. So all of this information are related to the redundancy. So this is used for the measure of the quality. So there are two ways to learn the normalization. One is informal way. Informal way means, first, what is a formal way? Formal means nice, dress up, fancy. Yes, that's true. Mathematics is the fancy subject, right? So formal means it's a mathematical approach. It's using equation. So in academia, when we are saying the formal approach or formal the opinion, formal something, that means it's a mathematical approach. Because it's clear, it's a fancy, nice. Okay? So that is a formal. Informal means non-mathematical, which means just to describe. Okay, forward. Like I explained that normalization is this. That is this informal way. So there are two ways of such a normalization. One is first, the informal way. Informal way we already explained in the measure of the qualities. So first guideline is if the database design is very well organized, is a very good quality, that means one table, one entity has only one meaning. In other words, if your database design, for example, I create a table as the ABC. I don't know what that means, but ABC includes the name of a student, and name of a department, and the department address, and the university address. That is not a good database design because it has several different meanings. Okay? In other words, it's a redundant information, which means it's not well organized. Okay? So that is the first guideline. To make the good quality of the database design, first one table has one meaning. Because of that, even though you didn't take this course before, so you can actually design your database, a very simple database, right? In the programming class or in your other class, software engineering class, I have used the SQL Server because I was able to create a table like the student and department and the course. That's it. Or the customer, transaction, whatever. Because you already intuitively know one table and one meaning, right? So this is the first guideline. Second guideline is, so this is an example of some well organized. So employee has only employee information. Department has the department information, and so on. The second approach is no insert, no delete, no update anomaly. What is the anomaly means? For example, this is the initial database design for company database. So employee underbar project is the table name. So that includes the employee number and project number as a primary key, and e-name, p-name, number of hours. Okay, this is our initial database. Using first guideline is also, this is not a good database design. Why? Because one table has employee information as well as project information. So this is not a good database design. Then this okay. Let's keep this one. The problem is, this is a sample data. So 0, 1, B, P0. 1, 1, 2, and project 1, and the pattern, and project name P1, and 20 hours. Okay? What if project 1 is done? Okay? Project 1 is done. So I'd like to delete all project 1. So remove this, remove this. What happened? All employee will be deleted together. Even though project is done, still employee is working for that company. However, because this is not a well designed the database. So in case one of the data is removed, deleted, all other information will be deleted together. This is called deletion anomaly. So something unusual activity when you delete the data. So this is a delete anomaly. In this case, okay, so I don't delete, I'd like to keep it. I'd like to update the data. Project name P01 is changed as it's a sample, for example. I changed the name, I'd like to update. Is it okay to change this? No, you have another project 1. So you need to update. When you update a certain data, you need to update all the data, several data, right? Why? Because this table is not well organized. So well designed. So this is called update anomaly. Okay. And I'd like to insert the employee in this table. To insert the employee, you need project, right? What if this employee is not assigned to any project? You cannot insert. That is called insert anomaly. Why this anomaly happened? Because database design itself is not good enough. So this is the second guideline. The first guideline, check whether one table, one meaning. Okay? And second guideline, whether there exists such an anomaly. Third guideline is as less as null possible. Okay? If you have a lot of null, that means there's something problem. Okay? Maybe something problem. So that is the third guideline. The last one we will see in the next class. It's a join. During the join, it caused some unexpected data. Okay, so we will see on Wednesday.